Hi all, my name is Michael Hendrick and I'm a recent graduate of Boston University, receiving a Bachelor of Arts in Computer Science this past May. Myself and my co-author, Manuja DeSilva, worked on and completed this project in the spring of this year.
Hi everyone, my name is Manuja and I also recently graduated from BU this past May with a degree in computer science, alongside my friend Michael. We had a great time working on this project earlier this semester, and today we're excited to share our solution with you all. This year's challenge focused on non-intrusive load monitoring, a process of observing changes in voltages and currents in a building and using this information to identify energy events concerning appliances within a building. This information is best analyzed and provided in real time. For our approach to the challenge, we use Apache Flink to assist us in managing the incoming data and to help streamline some of the work, so that we could better focus on other aspects of the challenge, such as the development of the algorithm for detecting events using DBScan. Our final solution, when testing on a dataset of 500,000 events, was able to achieve a vast reduction in latency and also reduce the total runtime by 86% while maintaining 100% accuracy. The second part of the solution, which entailed working with out-of-order events, also achieved better runtimes and lower latencies, although with a sacrifice to accuracy, more of which will be discussed later.
Apache Flink plays a pivotal part in the overall architecture of our solution. Apache Flink is a lightweight, open source framework and distributed processing engine designed for stateful computations over unbounded and bounded data streams. Out of the box, it includes features that cover a lot of the ground that one would usually need to consider when taking on a challenge like this one, such as processing incoming tuples and intelligently dividing those tuples into windows of fixed or dynamic size. In particular, Flink's built-in timestamp system and fault tolerance protocol provides developers a significant amount of trust that our data will arrive and be correct. To process our data, we take advantage of Flink's windowing APIs, which bunches our data, and then we use Flink's process functions to analyze information, make the relevant calculations on the raw data, and then send those features downstream to our event detection algorithm. Here, we can see an abstract implementation of a density-based spatial clustering of applications of noise, also known as a DBScan. DBScan is a popular data clustering algorithm that, when provided with the minimum amount of points and an epsilon value, returns clusters of which contain sets of our input data deemed to be similar to each other. These sets are also known as neighborhoods. Samples that do not belong to any cluster are assigned to a noise cluster. One can draw several metrics from each of these clusters, including its maximum member, its minimum member, and its temporal locality. These metrics are then further utilized to detect whether an event may be detected in that cluster.
Apache Flink is composed of various operators that transform raw data inputs, such as files, HTTP events, or sockets, into structured data streams, and we as programmers combine those operators to compute necessary logic based on the task at hand. This chain of data streams that encompasses these Flink operators is referred to as a data flow. The key components of our data flow are a sliding window that batches our data, the use of a process function to produce the active and reactive features from the incoming voltage and current inputs, and the use of a process function to run these features through our event detection algorithm. In particular, the use of sliding windows to batch our data streamlines our data flow greatly and works out of the box with Flink watermarks to ensure that all of our events have arrived in order if we so wish to optimize for accuracy. Sliding windows allow us to assign an unbounded stream of data elements into windows of fixed length. Sliding windows can be overlapping if the slide is smaller than the window size. This feature of Apache Flink allows us to automatically group the incoming voltage and current samples into windows of size 1000 without any further programming or intervention.
Process functions in Flink do the necessary low-level computational work to generate meaningful results. We use a process function inside our sliding window to calculate reactive and active power and to generate the tuples that our predict logic is expecting. In addition, we use a separate process function to call our predict method and emit the solution for each window to obtain the correct output. It is within this predict function that we run our implementation of the event detecting algorithm within the stream of voltage and current samples. The second query of the challenge had us devise a solution that could account for some events arriving late or possibly not even at all. Originally, we approached this by winning 20,000 time units to see if the events would eventually arrive, and if so, calculate per normal, otherwise we progress. Unfortunately, this led to very high accuracy despite the late arrivals, but led to higher latency in part due to the waiting and in part to how Flink handles the batching of data. Regardless, simply waiting was an unacceptable solution. Going forward, we decided not to wait for those tuples, and instead we fill in missing data with our own data. The data that we populate the incomplete windows with is based on the average of what has been seen up until things went missing, multiplied with some noise to create pseudo-random data points. When testing, we found that while this was not as accurate as waiting for incomplete windows, it was still detecting most events correctly with a profound increase of timeliness. This appeared to us as a reasonable trade-off and is the one we moved forward with.
After successfully completing both tasks on our local machines, we began to containerize the applications, only to realize that we had to create a custom solution different from the official Flink Docker container guidelines. These guidelines require that we run the job manager and task manager as separate containers. Jobs are composed of tasks, and tasks are individual pipelines to communicate with the job manager to complete an overall data processing problem. Due to the restrictions on the Docker Compose format, we packed the job manager, task manager, and application into one container. When the container is instantiated, it triggers the Flink cluster to start up. After determining that the greater infrastructure is ready, our application then submits its job to the cluster and then runs the prediction algorithm on the incoming tuples. After containerizing our application, we continue to tweak our solution. Throughout this process, we found some shortcomings in two specific areas. The first of which, when implementing the non-intrusive load monitoring algorithm as described in the reference paper, our implementation had a decreased accuracy when dealing with larger datasets. This decrease in accuracy was marked by detected events not listed in the ground truth. So, we came to believe that our algorithm and its underlying model were overfitted in some aspects. Second, although Apache Flink comes with many useful features out of the box that saves many lines of code when programming the processing of data, we were constrained to the limits of its batching system, and thus we were unable to reduce latency after a certain point. Thank you for taking the time to listen to our presentation on our work from this past semester. We'd like to open it up for questions and feedback at this time.